Okay, students, welcome to video class 43. In this video, we are going to do some more problems, that is state model numericals related to electrical system. So here is an electrical circuit given. Okay, you are asked to obtain the state model of the circuit. So before proceeding this, you should have an awareness of the circuit and the state variables. That's the most important thing of a state model. So look at this, you have a circuit with input u of t. It doesn't mean that this is a step. It is generally an input. It can be any inputs. So it's an u of t which is connected to a resistance R1 and an inductance L1. Then you have a you have a capacitor C and another inductor L2, and then at the output is taken across this R2. Now you have it's shown in the figure or in the question as a domain three variables are shown. That is, one is the inductant currents or the current through inductance L1, which is designated as I1, and that of through L2 is designated as I2, and while the voltage that comes across the capacitor is taken as Vc of t. Okay. Now, before moving into this, we should have an idea about what type of state variables we have. I've already mentioned about the type of one is it can be the physical variable form or it can be the phase. Now, if you represent the differential equation, the response and its differential equation differentials as the state variables, we call it as the phase state variable. And if you assume the physical variable as a state variable, like current and voltage across a capacitor or inductor, current through an inductor. Okay, so in this example we will be preferring the physical variable state variables. Now, how will you calculate the number of state variables? Now, as I have mentioned earlier in one of the videos, the number of state variables is equal to the number of energy storing devices, energy storing elements, energy storing elements. So, especially when you deal with an electrical system, then the first thing that you should note is the number of energy systems or the energy storing elements in the system. So you can see that there is two inductance and one capacitance. So altogether you have three energy storing elements. That means this will be equal to the number of the state variables. Now here the following are the state variables. One is the current flowing through what? Flowing through L1, right? The second one is the current flowing through L2, and the third one is the voltage across the capacitor C. And the current flowing is shown as I1, and this as I2, and this as Vc. Now, this is so these are the three variables that you can identify through each energy storing element. And if you can assign this I1, I2 and Vc to a state variable, and let us call that as x1, x2, x3. Okay, so this is the difference between the previous problem and this one. In the previous problem, what we did is we framed up a differential equation, and the output is assigned to the response is assigned to the response and its derivatives, and its first order derivatives are assigned as state variable. So there we can say that there we use the phase standard state variable, while in this problem or in this type of problem, especially in electrical system, we'll be utilizing the physical or physical state variable. So the physical variables will be assigned as the state variable. So you have three state variables, x1, x2 and x3. Now, some way or other, in order to get the state equation, what you need to do is you need to get as many equations as possible from this network. Now you can see that it is a two mesh equation, so you will be getting, you can apply KVL to both the loops, KVL to loop 1. Now when you apply KVL to loop 1, say if I am assigning in this way, right, the current in this form, I1, I2, okay, so when I write equation u of t is equal to, okay, u of t is equal to, if it would have been in this direction, I would have written like this, I1 into R1, but it is not I1 into R1, it is minus I1 into R1 plus, right, L1 minus L1 into di1 by dt, right? Then then again you have a minus Vc, right? You have a minus Vc. See, if say this is like this, say if you assume a current like this, say call this as I3, right? U of t is equal to I3 into R1 plus L1 into di3 by dt, and this is to plus to minus, so this will also be, it's just as a polarity of the drop, so this will be considered as plus VCT, but this is I3 is negative to minus I1, so all these becomes a negative sign. So okay, so it's clear, right? Now this is equal to I1 into R1, it is equal to U of t, or you can bring this to this side, okay, L into, you can bring this L into di1 by dt, L into di1 by dt as U of t, okay, minus U of t, right? Okay, so this will be, this can be written as Vc, V suffix c, plus I1 into R1 minus U of t, right? Okay, so you can write this equation as L into, what is di1, what is I1? I1 is x1, so what must be di1 by dt, that must be x1 dot, right? So this is x1 dot, L into x1 dot is, Vc is already assigned to be x3 plus I1 is assigned to be x1, so x1 into R1, right, and minus U of t, right? So what must be your x1 dot? So x1 dot will be R1 by L into x1 plus 1 by L into x3, 1 by L into U of t. So this is one of the state equation. Now what is what is the meaning of state model? Now the meaning of state model is to obtain state equation as well as the output equation. So so you got a part of the state equation as x1 dot. Now what is the next step? Now the next step is to find KVL or to apply KVL to loop 2. So when you apply KVL to loop 2, look at the direction of I2 and the polarity of Vc of t. So you can write this equation as Vc of t is equal to L2 into di2 by dt plus I2 into R2, or you can say that as to be L2 into di2 of t by dt is equal to Vc of t minus I2 into R2, right? Vc of t minus Ic of t into R2. Now what is this L2 into, what is this di2 of dt? We know that I2 is assigned to be x2, so the single derivative will be L2 into x2 dot, right? X2 dot, which is equal to okay, first of all let me write like this, minus I2. What is I2? minus I2, that is minus R2 into x2, right? I2 is assigned to be x2, and x3, Vc is assigned to be x3, so this is plus x3. Also, what will be your x2 dot? From that equation, you will get, we will be getting x2 dot as minus R2 divided by L2, R2 divided by L2 into x2 plus 1 by L2 into x3. Okay, so that's your x2 dot. So that's the second part of the state equation. Now one more equation you require, because there are three state variables, so you need three first order derivatives of the state variable. Okay, so you need to get x3 dot. Now how to get x3 dot? So I told you that get as many equations as possible. So there are only, two meshes, so the maximum possible equation from mesh equations you will be getting as 2. Now is there any provision to get one more equation? That is, you can also apply KCL, right? KCL at the node shown, at the node, at this node. Okay, when you apply KCL, what is KCL? KCL is the incoming current is equal to outgoing current. Now, as from this figure, since there are no current source directly connected to this node, all these current can be taken as the outgoing current. So the incoming current is equal to outgoing current, or the net current is equal to 0. So that means you can say that this is I1, right? This is I2, I1 plus I2 plus what is the current that flows through capacitance if the voltage across the capacitor is known. Now how will you find out that? We know that Vc of t is equal to 1 by c integral I of t dt, or you can say in the reverse step, from this you will be getting the current flowing through this as c into dvc of t by dt, right? So this must be the current. So this is equal to c into dvc of t by dt is equal to 0, right? Now let us assign the, let us write in terms of the state variables. I1 is assigned to be x1, I2 is assigned to be x2 plus c into, what is dvc? Vc is x3, so the first derivative will be x3 dot is equal to 0. So from this you can say that c into x3 dot is given as minus x1 minus x2, right? Or x3 dot is equal to minus 1 by c into x1 minus 1 by c into x2, right? So this is it. So we got the third set of the third part of the state equation. So you all got this x1 dot, x2 dot and x3 dot. Now let us frame up the matrix equation. So what is that? What is this state equation? The model of the state equation is x dot is equal to ax plus b bu, right? So ax plus bu. So you need to get that such a matrix. So you have a 3 into 1 matrix, right? Because there is 3 standard variables, state variables. So you can have x1 dot, x2 dot and x3 dot. So this is a 3 into 1 matrix. And since you have state variables, 3 state variables, so this x will be a 3 into 1 matrix again. So with x1, x2 and x3, right? These are the state variables. And this must be a big matrix, which is a 3 into 3 matrix. So you can complete that using these equations. So, right? So when you look at the x1 dot, so look at this, you have a part of x1, you have one part to be x3 and x2 is 0. So that means in the first row, the middle term will be 0. The other terms will be, one is r1 by L and the other one will be 1 by L, right? 1 by L. And when you come to the x2 dot part, you can see that the x1 is 0. So this is 0. Then x2 will be minus R2 by L2, minus R2 by L2, and this is L2, minus R2 by L2, and this will be 1 by L2. Now coming to x3 dot equation, you can see that you have no 3, right? So that is 0, while this will be minus 1 by C, this will be again minus 1 by C. So look at this is the equation, and this is the A matrix, or the system matrix, right, plus B into the input matrix. Now how will you find out the input matrix? Now you can see that, say, in the first equation only you have an input part, that is minus 1 by L is the coefficient corresponding to U of t. So this must be like this. This is again a column matrix of 3 into 1. Look at this. In order to get added, this product has to be a 3 into 1 matrix. Let us see that. This is a 3 into 3 matrix. This is a 3 into 1 matrix. So multiplication is conformable, so resulting in a 3 into 1 matrix. So the result is 3 into 1. So you require a 3 into 1 matrix into U of t. So fortunately we have only one U of t. In all other equations you can't find any U of t. So the rest 2 will be 0, and the other one will be, the coefficient is minus 1 by L. So this is minus 1 by L. So this is actually your state equation. This is the state equation, right? Right. Okay. Now, how to find out the output equation? Now this is not complete. State model will get completed only when you get the output equation. Now from the figure, y of t is the output, and y of t is the output that is taken across R2. So that must be y of t is equal to I2 into, so the current that flows through R2 is I2. So it will be I2 into R2, right? And what is the I2 is a state variable, right? Which is assigned to be x2. So this must be equal to x2 into R2, right? So in this equation you can see that, so when you write the state equation, right? Okay, state equation. Now what is the format of state equation? This is Cx plus du, where okay, so this is the output matrix C, and D is called as a coupling matrix. Now anyway, we can see that D is 0 because there is no the output, there is no input, so you don't have to worry about this part. So this will be our output equation for this circuit is of the form Cx. D is equal to 0 in this case, right? So X can be, what is that X? X is actually a 3 into 1 matrix. You have x1 and x2, x3. So this is a column matrix of 3 into 1 matrix, and if you want to get an output, okay, if you want to get an output of 1 into 1, you need to get this thing, right? So there is only x2 term, x3 and x1 is 0, so this is R2, right? 0, R2, 0. Now when you do the solution, when you do the multiplication, you're going to get x2 into R2. So this is the output equation, okay? And these two results in what? Results in the state model of this particular electrical circuit. Okay, hope things are clear. Okay, so you have the second question. You are again asked to find out the state model. You have a circuit like this. This is anyway, it's complete. Okay, this is like this. So this is plus a u of t, and I again repeat that this u of t has nothing to do with the step input. It can be any input. Okay, so u of t is a general representation as we use in state space. Okay, Now you have a resistance R, two resistance R like this, and a capacitance. V1 and V2 are the voltages that are shown across the capacitor. Now, as I told you, that the number of state variables always depends on the number of energy storing elements in the circuit. Energy storing elements, and as you can see that you have two capacitors, that means the state variables is 2. Now, the state variable that you can assign to these or the physical variables can be the voltage across these two capacitors, and they are V1 and V1 and V2, right? And V1 we assume it as x1, and V2 is assigned as another state variable as x2. Okay, now the next question is how to get the equation. Now we want V1, right? So V1 and V2. So as per the from this figure, you can see that you can, if you can perform, you have two nodes, right? So call this as node 1 and this as node 2. And if I can perform a node analysis on these two, you will be getting two different equations, right? So applying KCL at node 1, KCL at node 1, okay. So why I'm selecting KVL is because we require voltages, not the currents. So since these are two capacitors, so you need to switch accordingly. So as the problem varies, the approach will be varying. So in this problem, it's safe to apply KCL at the two nodes. Now when you apply KCL, you can see that no direct current source coming, so you can assume everything to be the outgoing current. Outgoing current is equal to the incoming current, and the incoming current is 0, right? So what must be this? So call this as V1. This must be the node voltage, or the voltage at this node, or this is coincidentally it becomes the voltage across this capacitor. Similarly, V2, or this is the node voltage V2. Now if you have this, when you write the equation at node 1, it will be V1 minus U of t divided by R. That's the current flowing through this branch, and this capacitor branch will be V1. Okay, so what will be your what will be your I2 now, right? So what is your I2? So this will be C into plus, next is V1 minus V2, V1 minus V2 by R, and what must be the capacitor current? What must be the capacitor current? We know that the current through the capacitor is C into dVc by dt. So this will be C into dV1 by dt is equal to 0, right? Okay. Now you can assign the variables V1 to be x1 minus U of t by R plus x1 minus x2 by R, right? Plus C into what is dV1 by V2. V1 is x1, so the differential of that will be x1 dot is equal to 0. So from this equation you will be able to get x1 dot, right? C into x1 dot, okay, is equal to bringing this to this side and separating the coefficients of these parameters. Say I'm going to, okay, let me bring this to this side. So this will be x1 minus U of t by R minus x1 minus x2 by R. And you can separate this out so that you will get this as okay, minus, and this will be minus 1 by R x1 minus 1 by R x1 will be minus 2 by R x1, right? And next is minus of minus, this is plus 1 by R into x2, and plus 1 by R into U of t, right? Okay, you can separate this like this. So this is actually your C into x1 dot. Now what will be your x1 dot? You can bring this to this side. So you're bringing RC, dividing everything by C, you will get x1 dot. So this is the first equation for this, the first of the state equation. Okay, now the next one is So by state model, I'm again repeating the same. You need to find out the state equation as well as the output equation. So the first part, we are doing the first part. Okay. Now to get the next equation, next set of equation, you can apply KCL at node 2. Right. When you apply KCL at node 2, this will be V2 minus V1. V2 minus V1 by R is equal to plus C into dV2 by dt is equal to 0, right? Now what is V2? V2 is assigned to be x2 minus x1 by R, right? Plus C into V2 is x2, dV2 will be x2 dot is equal to 0, or from this equation you will be able to get x2 C into x2 dot is, you can bring everything here, so that means it becomes x1 by R minus x2 by R, right? Or your x2 dot will be equal to, okay, x1 by RC minus x2 by RC. So that is your x2 dot, right? Now this is your x2 dot. Now you can have the equation of x1. So you got the first derivative of the state variables we have assigned, and we have understood that there are only two state variables, and we got that. And now converting it into matrix form, you will be getting this as x1 dot x2 dot, right? That is a 2 into 1 matrix, right? You don't have to write every time. I'm just explaining, that's all. So this is equal to a big matrix into a smaller one, and what must be that? That is actually x1. So this is x1, x2. So this is again a 2 into 1 matrix, meaning this has to be a 2 into 2 matrix. So let us do that. So the first will be minus 2 by RC. The second element will be 1 by RC. Coming to the second equation, it will be 1 by RC minus 1 by RC, right? Now, is it complete? No, because this x1 dot is having an input side. Now, do remember the state equation is of the form ax plus bu. Now, there is a u term in the first equation, while in x2 dot you don't have an equation like that. So anyway, the input is u of t, so you can multiply this by again a 2 into 1 matrix, right? In the first equation, you have a 1 by RC coefficient. In the second equation, you don't have any u of t. So this is actually your state equation. Now, what must be your output? Now, if I am going to take the output across this capacitor, your output is nothing but your y of t is actually equal to V2, right? V2, or in a sense, it is the voltage across this capacitor. Now we have already assigned V2 to be equal to x2, so this is equal to x2, or y of t is equal to x2, meaning you have y of t is equal to 0 1 x1 x2. When you perform this, you will get y of t is equal to x2. So this is your output equation. This is the output equation, and this one, okay, and these two, this matrix equation, this one and this one forms the state model of the circuit. Okay, so this is your question number 3. You're asked to obtain the state model of this particular circuit. Now, when you deal with the electrical circuit, you must first of all search for the energy storing elements. Okay, so the energy storing elements are, you have 3 elements, that is you have 3 elements, that is 1 inductance L and 2 capacitance C1 and C2. Okay, so these are the three energy storing elements. So therefore you can have the number of state variables as the current through the inductor and voltage through the capacitor. So I'm going to say the voltage across assign the state variables. Voltage across the capacitor C1 is VC1, V suffix 1, C1, and the voltage across C2 is V suffix C2, and the current the current through the inductor L is I suffix L. And I can assign these to some state variables, and I'm assigning it to be, say, call this as x1, this one as x2, and this one as x3. So altogether you have 3 state variables. So the number of state variables is equal to the number of the energy storing elements. Now the variables which we have associated with the capacitors will be voltage, and the variable associated with the inductor will be the current. So first of all, I'm going to apply KVL at loop 1. At loop 1. Now when you apply KVL at loop 1, you can see that u of t is equal to see this drop, this is shown as plus to minus, so this is VC1. You can straight away write like this, it is VC1. You don't have to write like 1 by c integral I1 of t and dt and so on, plus what is the current flowing through this inductor. So this will be I1, right? So I1 into or this will be L into d I1 by dit, and again a current I2 flows through against that, so that will be minus L into di2 by dt. Okay, so this is it. So you can call this as VC1 plus L into d by dt of I1 minus I2 is equal to u of t, right? So you can have this expression. Now you can have this this is I1 minus I2, right? Now looking at this expression, looking at this current through this L, what is basically the from the circuit, you can see this IL to be equal to I1 minus I2, right? Right? IL is the current flowing through this inductance. So the current flowing through this inductance, effective current will be I1 minus I2, right? So you can call this difference as IL. So you can rewrite this equation as VZ1 plus L into d IL by dt, right? Okay. So what you can say is this. So this is your equation. This equation can be written as u of t is equal to, what is VC1? VC1 we have already assigned to be x1 plus dIL. IL is assumed to be x3, or it is dx3 by dt, or this will be x3 dot. Okay. Now from this, so this is L into x3 dot, or from this you can evaluate x3 dot as minus x1 plus u of t, okay, or this is L into x3 dot, or x3 dot will be equal to minus 1 by L into x1 plus u of t into 1 by L. So yeah, this is your x3 dot. Okay, now you can have the second loop equation, that is KVL at loop 2. When you apply KVL at loop 2, this is loop 1 and this is loop 2. Okay, now this will be 0 is equal to 0 is equal to L into L into di2 minus I1 by dt, because in this loop I2 is the current, I2 is the main current, I2 minus I1 plus R into I2, right, plus VC2, right? Yeah, this is plus VC2. You don't have to write it as 1 by 1 by C into integral I2 dt. Instead of that, you have already assigned VC2 to be the voltage across the capacitor C2. So this is VC2, right? Okay. Now let us see how to write this equation. RI2. Okay. Okay. Now we need to do something for this I2, because in nowhere in this equation I2 is assigned, but we know that this is I1 minus I2, right? This is I1 minus I2. That's all. So you cannot substitute anything for this I2. But say, what is VC2? VC2 is something which we have assigned as X3. Now what is this VC2? VC2 is actually 1 by C integral I2 dt, right? I2 is the current flowing through this capacitor, so the voltage must be like this. Or what must be I2 from this? Assuming the C is a constant, you can write this as C into dVC2 by dt, right? From this you can find I2 to be C into dVC2 by dt. Now what is VC? VC we have assigned, VC2 we have assigned as X2. That means this can be written as X2 dot. Okay, so this is the substitution that you need to make for I2. So hope you understood. Now this we get from VC2. Okay, so so you need to be very careful in doing such problems. The approach will be differing on the circuits. Okay, so some way or other you need to get an equation in terms of the state variables which we have already assigned. If you are keeping like this, it will remain as such and you cannot do anything with this I2. So some way or other you need to relate with this existing or the available or the assigned state variables, so that when you coming to this equation, this becomes 0 is equal to L into di2 minus I1. I1 or I1 minus I2 is assigned to be X3, or this can be written as minus X3 dot, right? This is X3 dot plus what is R into I2? I2 is C into X2 dot, X2 dot plus VC2 is X2. Look at this, 0 is equal to minus L into X3 dot. We have already found it in terms of this. You need to, okay, so this will be minus X1 by L plus U of T by L, right, plus RC X2 dot plus X2. So what is your X2 dot? So from this you will be getting X2 dot as equal to, or RC X2 dot is equal to, okay, X1, right, then plus next is okay, so this is this will be minus X1, because you should bring this to the side, so this will be okay, minus to the side, and that becomes U of T by U of T plus U of T plus X2, right? Or you can write this X2 dot as equal to minus 1 by RC into X1 plus 1 by RC into X2 plus 1 by RC into U of T. So that is your X2 dot, right? So you'll be getting X2 dot. Now you need one more equation, that is x1 dot. How will you get that? Okay, now how to find out this x1 dot? Now we know that VC1, let us come to this VC1. What is this VC1 from the figure? From the figure, VC1 is a voltage that develops across the capacitor as I1 flows through this. So this will be, VC1 will be 1 by C1 integral I1 dt. Now you want x1 dot, right? This is your x1. Now if you want to x1 dot, you are actually differentiating dvc1 by dt. Now what is the result of this? 1 by c1, the derivative of d by dt of integral I1 dt, right? When you integrate, when you differentiate this, this is the differentiation of the integration of a function, and that is that function itself. So this becomes I1 by c1, right? So x dot is equal to I1 by C1, okay, right? Now we also know that I1 minus I2 is actually what? I1 minus I2 is x3, or I1 is equal to x3 plus I2. Now what is this I2? We have already seen I2 to be C into x2 dot. So substituting that, I1 is equal to x3 plus C into x2 dot, right? x2 dot. So that you can write this expression as, what is this? I1 is equal to, so from this I1 is equal to x3 plus x2. So x3 plus I2 by C1, right? x3 plus I2 by C1, or this can be written as x3 plus C2 into x2 dot by C1. Now what is this x2 dot? x2 dot is what we have already found out, the whole, this big equation. You can substitute this, you can substitute for x. So this is your x1 dot. So your x1 dot is equal to x3 by c1 plus c2 by c1 into, you will be getting this as minus x1 by rc2 minus x2 by rc2 plus u of t divided by rc2. This is 2, right? So there is a correction. I2 is C2 into dvc2. So that will be C2, 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 RC2. Okay. So this will be RC2. Okay. So rearranging, you will be getting this as minus x1 by R minus x1 by RC2 RC1, okay, minus x2 by RC1, right, minus x3 by RC1 plus u of t by RC1. So this is the expression. So you got the three expression, x1 dot, this is equal to x1 dot, and you can have the state equation as, you will be having a 4 into 1 matrix, right? Sorry, 3 into 1 matrix, x1 dot, x2 dot, and x3 dot, which is equal to minus 1 by RC1, minus 1 by RC1, 1 by C1, then minus 1 by RC2, minus 1 by RC2, 0, then you have minus 1 by L, okay, 0 and 0. So that's your x3 dot. So you can straight away represent those equations in the form of matrix x1, x2, x3, okay, plus another matrix is 1 by RC1, 1 by RC2 1 by L into U of t, right? Now what is your output? Output is VC2. Y of t is output equation is y of t is equal to VC2. Now we have already assigned this VC2 to be x2, right? So y of t is equal to is x2, or you can write like this: y of t will be 0 1 0 into x1 x2 x3. Okay, right? So this is actually the state model of the day. So from this problem, it is understood that the approach will be different for each case. So you must be very careful in assigning the state variables as well as the relationship to arrive at. So there can be some situations where, as we have done here, say for example, you may be coming across a situation where you have two dots. So now in this, we have already found out x3 dot. So some way or other you will have to make it into a equation having only one differential, one single order differential equation. So a proper substitutions have to be made in order to, our objective is to get the first order derivative of the state variables we have assigned in terms of the state variables and the input. Okay, so that means that particular equation should not have any other first order derivatives. That's the logic. So you need to do the proper substitution. Okay.